So we're in chapter 6 now on public key cryptography, and last time we just talked about some of the the nature of public key cryptography, mainly how it's different from symmetric key cryptography because there's two keys for each person instead of one key for each pair of communicating parties, and each person has a public key which anybody can use to encrypt a message to them, and everybody has a private key, which is what you need to actually decrypt those messages. So it's kind of like a mail slot. Anybody can put a letter in, but only the homeowner can open the door and read the mail. So to see how all of that stuff works, we have to do a lot of number theory. So we're gonna just get started on that today. So I had planned on just like writing in this notebook much the way I would write on the board if we were in class. So I want to start with the absolute beginnings. So let's talk about divisibility. Everything here is going to be an integer. So z is integers, so that means positive and negative whole numbers. And if you can't read my handwriting, please yell at me and ask questions and stuff like that. And eventually I will not be writing sideways. You just have to get used to this. So here's some notation. So if I write D and then a vertical bar and then A, so both of these are integers, integer D and integer A. So what this means is that D divides A. And so what does that mean? That means that A is equal to K times D for some integer K. And so what are examples? 2 divides 4, but 2 does not divide 5. And 6 divides 36, but 6 does not divide 100. Am I right about that? Yeah, that's right. Okay. All right. So here's something that's kind of interesting. Is it true, you guys tell me, is it true that 22 divides 0? You can use the notation. I'm sorry, the definition. This is the definition. So is it true that 0 equals K times 22 for some K?
Yes.
Yes, and what is
If K is 0?
That's right. That's right, yes. And so it's true that every number divides 0. So every number divides 0. Okay, all right, so that's an important fact. And now, is it true that 1 divides 1, 2, 3, 4, 5? Let's see. So is it true that 1, 2, 3, 4, 5 is equal to K times 1? What is K here?
1, 2, 3, 4, 5?
Yeah, 1, 2, 3, 4, 5. Okay, so this is true, and of course it's true for any number. 1 divides every number, every integer. Okay, so 0 and 1 are kind of opposites because, let me just write it in notation here. Okay. So for all D, so for all integers D, it's true that D divides 0, so every number divides 0. And it's also true that 1 divides D, because 1 divides every number. But there's only one number that divides 1. What is the one number that divides 1?
1?
1, yeah. So there's only one number that divides 1, which is 1. And there's only one number that 0 divides. What's the only number that 0 divides?
Probably 0.
Yeah, that's right. Okay. So you can see that 0 and 1 kind of have opposite properties. All right. Okay, so we're going to be doing a lot with prime numbers. Let me go to a new page here. So P is prime if D divides P implies that D is equal to P, or D is equal to 1. So in other words, there's only two numbers that divide a prime, just itself and 1. And everybody probably knows lots of examples, like 2, 3, 7, 11, 13, 17, 19, 23, 29, 31, etc. How many primes are there?
Infinite, right?
No.
Are there finitely many primes? They seem to be sort of spacing out here. Like these are pretty close together, but then it seems like there are sort of bigger and bigger gaps maybe. So maybe they just peter out at some point. But it turns out that they don't. So there are infinitely many primes. And this is one of the oldest and most beautiful proofs, which I hadn't planned on doing, but maybe we should do it. There are infinitely many primes. So the proof is, given any list of primes, you can produce a given any list of primes, you can produce a number that is not divisible by any of those primes. So if you have a list of primes, P2, P3, let's just say that there are 3 of them, because we don't have to be super formal here. So suppose that somebody claims that there are only 3 primes. Then you can produce a new number, P1 times P2 times P3 plus 1, okay? So now let's just think about this number here. So what is n? N is congruent to blank mod P1. What goes in the blank there?
2.
All the prime numbers.
No, what I'm trying to get here is that this number is evenly divisible by P1, right? And so the remainder, when you divide out P1, is 1. And for the same reason, n is congruent to 1 mod P2, and n is congruent to 1 mod P3. And so none of these primes divides n. That's because if a number divides another number, then, you know, if D divides A, then what does that mean? A is equal to K times D, and then A is congruent to 0 mod D. And so a number is divisible by another, and so D is divisible by A means that A is congruent to 0. So so none of these are zeros. So n is not divisible by any of these prime numbers. We could have done the same thing with more primes, you know, up to any finite number of primes. So if you have any finite list of primes, you can produce a number that is not divisible by any of those primes. So then what could n be? It's either a prime that wasn't on your, it's either a prime that wasn't on your list, or else it's divisible by some prime that's not on your list. So this means that your list was not complete. So there's no finite list of primes that's complete, because you can always produce something that implies that the list is not complete. Therefore, there must be infinitely many primes. Okay, so Here's an important fact which you have probably seen before. Unique prime factorization. How many people have heard of this before?
Sounds familiar.
So what it's saying is you take any number. Somebody want to just name a number?
7.
Not 7. 7 is prime. Pick an in, like a, it could be big. But 7 is a good example. So 7 factors uniquely into primes as 7. How about, let me pick one to get us started here, 28. So 28 is 2 times 2, that makes 4, times 7, which I can write as 2 squared times 7. So I've written 28 as a product of prime factors. And the primes are unique. There is no other way to express 28 as a product of other primes. So so it has 2 factors of the prime 2 and 1 factor of the prime 7. And let's look at 24. 24, it's kind of interesting, right? Because it's can you guys do this in your head? I'm thinking of it as 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. I think this is it. So 24 can be uniquely expressed as a product of primes as 2 cubed times 3. So 2 and 3 are prime. So this is true for any number. And so the way you would express it, like in jargon, is any number, any integer n can be written as p1 to some power times p2 to some power times pk to some power, where p1, p2, blah, 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 pk are prime. And it can't be written as a product of primes in any other way except by rearranging the order in which these come. So, if you write the 3 first and then write the 2, that's not interesting. So it's unique product of primes up to rearrangements of the primes. And maybe we can just play around a little bit inside one of these many terminal windows. Let me clear this. Are you guys seeing a little terminal window now?
Mm-hmm.
Okay, cool. So just from the command line, you can factor numbers. So that number that I just made up is 3 times 7, and it turns out that 6284675 is a prime number. And you can play around with this and see how big a number you can type in before it gets really angry at you. But every number can be written uniquely as a product of primes. Okay. So now we're going to go back to this little notebook, and we'll start a new page. And let's talk about divisors. So the divisors of n is the set which is all integers d, such that d divides n. And usually we only consider the positive ones, so you might want to do a plus here. So if 2, let's consider this. So 2 divides 6, right? And that's because 6 is equal to 3 times 2. But also, -3 times -2 is also equal to 6. And so it's also true that -2 divides 6. So anytime a number has a divisor, it has a positive, there's a positive one and a negative one. So we'll just write the positive ones. So let's look at some examples. How about, for some masochistic reason, I picked 255. The divisors of 255 are 1, I guess I should actually try to write this in a somewhat precise way. So 1, 3, 5, 15, 17, 51, 85, and 255. Okay. So these are not all prime. So what's an example of a number on this list that's not a prime?
15.
Yeah, 15 is not a prime, right? So which ones are the prime factors? So there's 3, 5, 1 is always there. 17, 51 is not prime. Why is 51 not prime? Because
It
it's
is
divisible.
divisible by 3.
Yeah, exactly. So you know if the sum of digits are divisible by 3, then the number is divisible by 3, so it's divisible by 3. So 255 only has 3 prime factors, which are 3, 5, and 17. But then, like, what is 51? 51 is probably like 3 times 17, right? If I had to guess. So this is 21. Yeah, right. That's right. So 51 is 3 times 17. So, but it's still true that, so what is 255? It's actually, I'm going to just get the factorization really fast and then tell it to you. Factor 255. So 255 is actually 3 times 5 times 17. So 255 equals 3 times 5 times 17, but then what's going to divide that? 3 and 5 and 3 times 5 and 17 and 3 times 17 and 5 times 17. And is that all? So this one is 15, 17, 3 times 17, 5 times 17. Oh, and then the whole thing, right? It also divides itself, 3 times 5 times 17. So that's where all of these divisors are coming from, just different combinations of the prime factors of the number. Right. Okay. All right. So now we'll talk about common divisors. So the common divisors of two numbers A and B are just the numbers. I'm going to write CD here of A and B. This is the set of divisors of A intersect the divisors of B. So it's just the divisors that they have in common. So for example, if A is equal to 480 and B is equal to 255, the common divisors of A and B is equal to 1, 3, 5, and 15. So if you factorize them, it's easy to figure this out. We already know that 255 is 3 times 5 times 3 times 17. And then what is 480? I'm going to factor it really fast and then come back to you. Factor 480, that is, whoa, 1, 2, 3, 4, 5. It's 2 to the 5th power times 3 times 5. 2 to the 5th times 3 times 5. So now, of course, they are both divisible. Somebody talking? They're both divisible by 1 and by 3 and by 5 and also by 3 times 5. So those are all the common divisors. So if you factored two numbers, then it's easy to figure out what the common divisors are. You can just figure it out from the prime factors. Okay. Now we can also talk about the greatest common divisor. So the GCD of A and B is the greatest common divisor. And this is just the biggest divisor that they have in common. So for these two numbers, what is the greatest common divisor? Wake up. Here's the common divisors. Which one is the biggest number in the set?
15.
15. Yeah, so it's 15. Okay. So you guys have spent a lot of time in 204 talking about common divisors. So some of this is going to be a little bit of a rehash. What algorithm do you use to find common divisors?
Euclidean? No, not that one.
Yeah, the Euclidean algorithm. That's right.
Is it?
So there are other algorithms. Let's do a dumb algorithm for GCD. So let's say A is equal to and B is equal to and we factor A. Whoops, sorry. Factor A, and we factor B. Okay. So what would you say is the greatest common divisor of these two numbers, A and B?
That one and that one.
Well, do they have any prime factors in common?
Huh?
Yes.
No, then it has to be,
DNA.
yeah, then the GCD has to be 1, because if they have a
Oh,
factor in common, then it's either, you know, if it's not 1, it's got to be divisible by some prime. And so the GCD of these two numbers is 1. It's easy to find the GCD of two numbers if you already have them factored.
Just compare them.
Yeah, you can just look at the prime factors and see which prime factors they have in common. And it's like the biggest part of their prime factorizations that they have in common is the GCD. But you know that factoring is kind of slow. So factoring numbers runs in time that's like, this is not exactly right, but if you let me go, what are you guys even looking at? I'm not even sure. Oh, you're looking at the terminal window right now.
Mm-hmm.
So come back here. So if you want to factor an n bit number, how long does this take? So the fastest known algorithm for doing this is called the general number field Sieve. And so you can read the Wikipedia article. I have to spell Sieve here. Do you guys think it's E before I or I before E? Sieve?
I before E.
Probably
Yeah,
I'm.
you're right. I knew Shana would know that. Sieve. Okay, the general number field Sieve. It can do this in time that's proportional to E to n, the cube root of n. This is not exactly right. There's also a logarithmic term in the exponent that I'm ignoring that isn't very significant. So this is kind of interesting because it you know it's not exponential time because of the cube root on the end. So it's faster than exponential time, but it's also slower than polynomial time. So if you guys have had, I know probably not many people have had Calculus 3, the way we do it at John Jay, it includes like, you know, you would take like a, I don't know, we could do this. What is the limit as n goes to infinity of e to the cube root of n over any polynomial and n here. So p of n just stands for any polynomial. So this is going to be a little bit hand wavy, but you remember L'Hopital's rule? You know, this goes to infinity, that goes to infinity. So the limit is the same as if you take the derivative of the top and the bottom. So we're not going to do all that, but let's say that this is a degree 100 polynomial. So what happens if we take 101 derivatives of a degree 100 polynomial?
101. That's 0.
Yeah,
right?
0, right? So eventually this becomes 0 on top, and this is non-zero on the bottom. I'll just write not 0 down here. So 0 over not 0 is equal to what? 0.
Yeah.
Yeah, 0.
I had to
So,
think about
so,
that.
so what we just showed in this kind of hand wavy way is that this thing grows faster than any polynomial. But it also grows slower than 2 to the n. So it's sort of, this growth rate is called super polynomial, but it's sub-exponential. A lot of the functions that seem to be useful in cryptography are kind of like this, but you know, if there's no algorithm there seems to be no algorithm that factors numbers in polynomial time. It seems to take this sort of sub-exponential time. So this blows up really fast with n. And so you can only factor small numbers. And I think the biggest number they've ever actually factored is like 700 or 800 bits right now. And for cryptography, you tend to use numbers that are like, I don't know, at least 2048 bits. And the reason we have to use numbers that are so big in public key cryptography is we want the number of bits to be way so big that this number is huge. And so nobody can factor a number by brute force. Okay. That was a little bit of a digression. So let's
factor over a number over 700 on a modern
no,
computer.
you can't factor a number with more than 700 bits.
Oh yeah.
So yeah, so that's a number that's like in the range of, you know, 2 to the 750 or something like that. We can look at a number that's that big just for fun.
That's ridiculous big.
Yeah, it's really silly big. So you can just do Python is really good because you can make integers as big as you want. So 2 to the 750 is like a number about that big. And then the numbers that we often use are like numbers kind of like this, about that big. And if you did the exercise earlier in the semester, which we eventually all have to do about setting up your public key, maybe I can even just remember how this works. SSH keygen. There it is. If you generate a key for the purposes of public key cryptography, let's just save this in temp blah. Okay, so now if I do cat temp blah, so this is encoded in something called I think it's just encoded in base 64. It might also be encrypted with the empty passphrase that I gave it. But just from how long it is, what it basically is that it's one factor that's about as big as this, and then it's another factor which is about the same size, and that's sort of the content of this file. You can see the length is about right. Okay.
It merges those two things.
Yeah, it's just like it has to store excuse me, two numbers that are about that big.
Yeah.
Okay, so let's come back to GCD and Euclid's algorithm. Man, just having a sneezing fit here. You know, it's spring for sure. Okay, so I was going to at some point show you a worksheet here on CoCalc, and we can maybe just go there right now. And I tried to give this to you. Let me just make sure that it got copied to everybody. So it's called GCD, and it's in the activities folder, and we can all go there right now. And it's called divisors.sage. Okay. All right. So this is Sage. Sage is great for these number theory things, and there are functions already built in for GCD and divisors, and I wrote a little function to do common divisors. It's thinking.
Kind of like what the terminal does.
Yeah. It's just it also it supports more functions. Really, all the terminal can do is just that one factor trick. It doesn't know GCD and stuff like that.
So what you're saying is you're smarter than Bill Gates.
Man, Bill Gates hates that terminal because that's Bash, but because that's a Linux terminal. But actually, they've started putting a Bash terminal inside Windows, which might actually make me go back to Windows. You spend a lot of time figuring out how to do everything from the terminal, and then you can't use it, and it makes you don't like it. But now, if they're going to put one of those in Windows, then maybe I'll take a look at Windows again. So here's a couple of numbers, A and B. I don't know if you guys can see. I'm going to make this bigger, and you can open it on your own too. So these are just two numbers that I quickly made up. A is about 30,000 and B is 517. And here are the common divisors. So what I want you to observe here is that the common divisors of A and B is a subset of the divisors of their difference. So 1 and 47 both show up on this list down here. So let's do a quick proof of that fact. Come back here to the notebook page, and let's start a new page. And we'll say if D divides A and D divides B, then D divides, let's say A minus B. Really, it divides any linear combination of A and B, but let's just say this one first. Okay, so let's do a little proof. So what is, when you're doing proofs, I know you guys are just starting out with proofs because this is, 300 level undergraduate class, but do you remember the definition? When you're proving something, you always start with the definitions. Remember the definition of this statement, D divides A? That meant what about A? A is equal to?
K times D?
Yeah, something times D. Let's call it K. And this statement means that B is equal to some other number times D. Let's call it L. So then if I look at their difference, A minus B, this is equal to KD minus LD. And you can factor out a D, and this is K minus L times D. You can call this some other number, like M or something. So it's equal to MD. Now, if you look at just this part, A minus B is equal to M times D. That means D divides A minus B. So everything that is every common divisor of A and B is a divisor of their difference. And so this trick that we used, it would actually be true for plus also. If I change this to plus, then I would change this to plus, which would change this to plus, which would change this to plus, and the same statement would still be true, right? Okay, so let's sort of write that down. So if D divides A.
Why would it be the same for plus?
Because you can factor out numbers across a sum. So now we have a sum, and you can factor out d from the sum. Before we factored it out from the difference. You
Okay.
made me so ashamed, Aiden, because you made me realize that I'm teaching this really terribly.
No, it's not that. It's I was just confused at where we were going.
But you're right. Okay, sorry. And then d divide, and so if d divides a and d divides b, then d divides also a plus b. So it divides really any linear combination of a and b, such as their difference or their sum or something. Now I want you to consider this other situation, all right? So right now we have like a, let's come back here. We have that the common divisors is a subset of the divisors of the difference, all right? We're headed toward Euclid's algorithm, all right? Just be strong. We're gonna get to someplace good and familiar in just a minute.
Discrete.
Yeah. So now suppose that d divides b and d divides a minus b. Then d divides a. So let's try to give a proof here. So look at the assumption. We're assuming that d divides b and d divides a minus b. Then by what we did above, d must divide the sum of those two things. So d divides b plus a minus b. Why is that? That's just because of this statement, which I was hoping we would all agree was true. And this is just exactly, drum roll, what is it equal to, this stuff?
D is equal to.
Something cancels out here. Can you read that?
It's the B, right?
Yeah,
It's
well, it's
A
just
left.
A. Yeah, it's just A.
Yeah.
So this is just A. Okay, so then what we've shown is that D divides A, and that's exactly what we wanted to show. All right, so now consider the common divisors of A and B. So this is the same thing as the common divisors of B and A. It doesn't matter which ones you write first. And now I claim this is the same thing as the common divisors of B and A minus B. And okay, so these two statements that we just did prove that. So if D divides B and D divides A minus B, then D divides A. So that means any common divisor here is going to divide both B and A. So it means it's a common divisor there. Okay. In the other direction, we showed originally that if D divides A and D divides B, then D divides their difference or their sum. So that gives you the other direction. So everything that's a common divisor here also divides that difference. And so these two sets are equal. Okay, and this is the fact that provides the gas for Euclid's algorithm. This is what makes it go. So now what I can do here is so what did I do? I had B and A, and then I took B away from A. So I just subtracted the first coordinate from the second coordinate. But because that was true the first time, it's going to be true any number of times. So I can, now just let this be a new variable like A or something, and now this is going to be equal to CD of B and A minus B for the same reason. But if I stick with lowercase a, this becomes A minus 2B, and this is the same thing as B and A minus 3B, and so on as far as I want to go. So what I can do is I can subtract out all the number of times that B goes into A evenly, and I can just leave behind the remainder. So eventually the only thing that's left here is the remainder when you divide A by B. And so this means that it's equal to B A mod B. Okay, so just to summarize what we just showed, we showed that the common divisors of A and B is equal to the common divisors of B and A mod B. All right, so this lets you, so it's also true then that the, you can just add a G here. So then the biggest one in that set must also be equal to the biggest one in that set, right? So the greatest common divisor of A and B is equal to the greatest common divisor of B and A mod B. So this is basically Euclid's algorithm. Let me see if I can, I wrote this up in Python. And so I'm going to try to share it with you. Let's get a terminal window here. Okay, so here we are. Locate gcd.py, and there it is. Let me just dump it to the screen. Okay, so here's the code. Can everybody see that?
Mm-hmm.
So the GCD of A and B, you can print them out. But it's it's a really simple recursive algorithm. So if B is equal to 0, then it says return A. Otherwise, it does this recursive step, which is to return B and A mod B. So we just justified that. So we showed that the GCD of A and B really is the GCD of B and A mod B. That's what we just proved. But why do we stop if B is 0? So do you remember what the divisors of 0 again are? What are the divisors of 0?
0.
0 divide, no, yeah. So 0 divides 0, that's true, but what else divides 0? Does 5 divide 0? Is 0 equal to k times 5?
Yes.
Yes. So
Anything divides 0.
that's right. Every number is a divisor of 0. So the greatest common divisor of 0 and anything is just that other thing. So that is why you have this case here. As soon as B is equal to 0, and eventually B will be equal to 0 because you keep doing these mods, and eventually B will just go into A evenly. So let's watch this go. So we'll just do Python 3, and then okay. So what happens? So we start off with the two numbers, and then this one gets copied over here, and this one gets copied over there. When did that happen? I don't know. Go ask your mother. Oh, okay, right. I actually do understand why.
Wait, what?
Oh, is that an insult? I was actually talking about Dr. Seuss. Have you ever read Red Fish, Blue Fish, or Two Fish, Blue Fish? What is it?
No,
I read this to my daughter all the time. It says, not one of these is like another. Don't ask me why, go ask your mother. And there's another line where it says, like, I don't know, why is this creature look like a lollipop? I don't know, go ask your pop. So sorry, that was not an insult, that was a Dr. Seuss. Yeah.
I thought you were testing if somebody was listening or not.
Okay. Now I kind of want to insult everybody, but I've already said what county I live in, so I better keep it under control. So the reason that they got swapped here is because one of them is smaller, right? So originally this number was A, and A mod B. So B went into A 0 times with the remainder of A. So see how that worked? So what it just did is it put the biggest one first, the first time through this loop. And now this one comes over here, and you reduce this one modulo the other one to get 8455. And then this one comes over here, and you reduce that one modulo the other one to get that number. And then this one comes over here, and you reduce that number modulo the other one to get this number, and then and so on and so forth. So this the thing that makes Euclid's algorithm so cool, and it's amazing that it's such an old idea. You know, it's truly ancient. It's like at least 2,500 years old, and it's probably older than that, because Euclid is probably just the guy who wrote it down. It's probably known, you know, from time, and maybe at least maybe 500 years before that. Who knows? But look how many steps it takes. It takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this isn't exactly true in this case, but the running time of Euclid's algorithm is approximately the same as the number of digits that you are trying to find the GCD of. So 1, 2, 3, 4, 5. So it's not exactly right, but it's approximately right.
In
so
what
what is-
unit? In like seconds or microseconds?
it's just the number of numbers. So like
Oh.
this is a 5-digit number. And so the running time is approximately like 5 steps. It turned out to be actually 10 steps, but it's the same order of magnitude.
Like however many times you need to run through the loop.
Yeah, and so I mean it's also the number of bits in the number, but this is just like a question of a constant factor. You can also think of it as the number of bits in the number. So with these big numbers that we were talking about before, like these 4,000 bit numbers that we were discussing, like 096. So we might be working in cryptography with a number like that, and it has a certain number of digits. We could actually figure out how many digits it is if we care. So it turns out to be, oh, fun. 1, 2, 3, 4. Oh, there's probably a nice math puzzle there.
That's gotta be on purpose.
So it turns out to have about 1,000 digits. So you can take the GCD of really big numbers really fast, because Euclid's algorithm is an extremely fast algorithm. Like, you know, something runs in logarithmic time. That's about as fast as you ever get. So I could take 2 enormous numbers and still find their GCD extremely quickly. So that's good. Now, the reason, or one reason, that we care so much about GCD is because it lets us find modular inverses. So maybe we should set this up as a question. Let's take 2 numbers that are relatively prime. Actually, we still kind of have them around, I guess. A and, whoops. Oh, sorry. What were these numbers? A and B. So B is a little bit less than A. And we factored these numbers. And I don't remember exactly what the factors were, but here they are. So they have no prime factors in common, so that means their GCD is 1. So you might remember that when we're going to explain all this again from start. So if you don't know what I'm talking about, just let this sink into your brain right now. So if 2 numbers have no factors in common, no divisors in common, and no factors in common, then their GCD is 1. And in that case, the multiplicative inverse exists. So just put that in the back of your mind, maybe. We want to find the multiplicative inverse of that modulo that. And let's just go do it in Sage. So let me take us back over to the Sage worksheet. By the way, in Sage here, I work through, we just take two random numbers and then look at the common divisors, and the common divisors of a minus b is the same. Common divisors of a minus 2b is the same. Common divisors of a minus 3b is the same. Common divisors of b and a mod b is the same. And then there's an exercise for you if you want to do it. But sorry I keep getting texted. Should have turned that stuff off. Let's say that this is A and this is B. I hope I'm not reversing them. Okay, let's just make sure these are loaded up here. All right. So what we want to know is, what is the inverse inverse mod? So what is the inverse of A? Which one is the smaller one? B. Okay, so this will be the interesting question. What is the inverse of B mod A? It says that number. What should we call that? B inverse. And so what makes B inverse the inverse? It means that if I do B times B inverse modulo A, what should that be equal to?
Mm,
1. Okay, so since I got off on this track, I feel like I have to stick with it. So let me come back and just remind you about modular inverses with smaller numbers. Jesus Christ, man. Here, let me switch the page. So let's just look at the numbers mod 5, so Z5. Let's actually look at the multiplicative group. So this is 1, 2, 3, 4. So every number here has an inverse. So what does it mean to talk about 3 inverse? So whatever this number is, it has the property that 3 times 3 inverse is congruent to 1 mod 5. So this is the inverse of 3 mod 5. And does anybody know what number this is from this group?
6.
Yeah,
That
that's
one number?
right. So you want to get to 6. So what do you multiply times 3 to get to 6?
2.
Yeah, exactly. So 3 times 2 is 6, which is congruent to 1 mod 5. It's so distracting. So the inverse of 3 is 2. God damn.
You not have a silent mode on your phone?
I've just been hoping it would stop. I'm going to turn notifications off. Okay, so we just did exactly the same thing, just with bigger numbers. So what we just did is we figured out, and the notation that we used from the Sage worksheet, we figured out B inverse mod A. So let's go back there and try to understand what we just did in those terms. So here's A and B, and so we got the inverse of B mod A. So what is it that makes it the inverse? It's the fact that B times B inverse is congruent to 1 mod A, which is what this is saying. Okay. All right. So I feel like maybe we should just stop here, because what we're going to learn now is basically how to compute what I just did using Sage Magic. And it turns out that the way you compute it is by using something called the extended Euclidean algorithm. Did you guys do that in 204?
I did.
Okay, cool. So you've already seen the extended Euclidean algorithm. So if you really want to know what we're going to talk about, you can just look at your notes from 204 or read the textbook. So for the rest of class, I can take questions, and or you guys can do this exercise. You want to try to do that exercise? I already have the numbers typed in for you. You have this in your CoCalc now if you want to do it. I can also answer questions on the homework or the midterm. Okay, right. And just as a reminder, I'll be here in the same room at 11 a.m. tomorrow in case anybody has any questions. I'm probably going to end up helping several different people at the same time, so hopefully that's okay.
Yes.
All right. So I hope you guys are staying healthy. Shayna, especially, keep us posted since your brother who lives across the hall from you has coronavirus.
Hopefully I will be able to keep you posted on Thursday.
Yeah, I hope he's okay. And also, someone else had a friend that had coronavirus, and I hope that person does well. Anybody else know anybody who has coronavirus?
Not that I know of.
Yeah. Well, according to Governor Cuomo, we can just wait. You know, like we're all gonna get it. So it's just a matter of time.
80%.
Yeah. You know, I read his comments. What he actually said was 40, 60, 80%. It wasn't like he went right to 80, you know. He started at 40 and then went up to 80, but it's still scary. Okay, so let me just take the attendance here. It's the 24th, and some of these, if you can't talk, chat, and I'll try to look over here at the list of attendees and get you that way. But if I can't, just let me know. So Shipu, are you here?
Yeah.
Got you. Aiden is here. Tall?
Here.
Great, got you. Fernando?
Yeah.
Got you. Lewis?
Here.
Got you. Andy?
Here.
Got you. Sar is here. Gibran is here. Tussadak?
Yes, I am here.
Got you. Omaru? Is that another seagull? Omaru, are you here? I see you there. I'm gonna mark you as present.
Can you hear me?
Yeah,
There you go.
Oh, sorry. I have an issue with the mic.
I got you. Adam?
He just chatted.
Okay, yeah, I see him there. And Shayna is here. Andrea?
Here.
Got you. Samson? Got, okay, I'll assume that's Samson. And I see him there. And Jake?
Yeah.
Okay, got you. Sylvia? Let's look and see. Yeah, Sylvia's here. David?
Here.
Got you. Serene? I don't see Serene on the list. Anybody know about Serene? He also missed last time. I think he might have something to do right now. But he can watch the recording. Okay, Raul? Nikita? Got you, Nikita. Aaron? Got you, Aaron. Fabian? Got you, Fabian. Raymond?
Here.
Got you. And Matthew?
Here.
Got you. Catherine? I see you. Okay, good. And Ella Lowy?
Here.
Got you. Okay, awesome. All right, so I hope everybody has a great week. How are your other classes going? Are you okay or a complete disaster?
Okay.
I have another one in like an hour.
Yeah. Okay, well, I hope things are going well, and I'll see some people tomorrow and everybody on Thursday. So
I just have a quick question because
Sure.
my internet was lagging out in the very beginning and I couldn't hear what's the thing that's happening at 11 a.m.
Tomorrow I'm just gonna have like an office hour, right back here in this room.
Okay, so the same chat code.
Yeah.
Okay, cool. Thank you.
Same link too?
Yeah, same link.
Okay.
And I'll try to always do things here. I understand Zoom better than I did last week, and this room is just you know, my room, so I'll just open it.
Okay.
Thank you,
Okay.
Professor.
All right. Okay. Bye. Thank you. See you next time.
Thank you.
Bye.
Yeah.
Bye.
Bye. Thank you.
Bye.
Bye.